Okay, and we'll begin the formal part of the evening with acknowledgement of the country. So I'd like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Gallagher people of the Ordination. As we share our knowledge, teaching, learning, and research practices within this university, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianships of the country. And it is my pleasure to introduce tonight's speakers, Gordana. And Gordana is a statistical consultant and research fellow at UNSW Sydney with research interests in modeling and visualizing multivariate discrete data. So today we're going to hear a little bit about her key research interests. And of course, in her spare time, Gordana would like to, well, can be found in hiking and also ocean swimming enthusiastically. No, I want to leave out that part. All right, and in that case, please join us welcoming Gordana.
Thank you, Thomas. I'm sort of juggling two screens here, so I'm not sure what I'm going to do, but hopefully you can hear me. At some point, I'm going to ask you. No, but yeah, they should be able to hear from there, right?
Yeah, sure.
That'll be all right. At some point, I might ask you to put something in the chat, so be ready for chats. All right, so apologies for the really lame title. It was very late at night when I had to come up with the title for this. How do I do that? All right, so just to start with my acknowledgements, I work on and live on the lands of the Gadigal and Badigal peoples. I work a lot with collaborators. Everything I do with a bunch of people, mostly David Wharton and Francis Way. And so they were involved in all this work, but the visualization stuff was also Diane Cook and Francis kind of started this collaboration. And thanks for the EcoStats Research Group and the School of Maths and Stats Central, the Australian Research Council, and most of all, of course, Our Ladies, and I should have put Our Ladies on there, Our Ladies and the Stats Society for inviting me to give this talk. Okay, so I'm going to start with a little bit of motivation. It's an interactive sort of thing, so you have to put up your hand if you're here, or if you're not here, you have to type into chat, and it's not hard. It's just a very easy test. Okay, pass or fail. All right, so not everybody is familiar with residual plots, so I wanted to just give a little idea of what the right answer is, okay? So when you fit a model, sometimes you need to check if that model is appropriate, and you might do a residual plot. And so the one on the left is kind of what you're looking for. You kind of want this mess of points and nothing, no pattern. The middle one's no good because there's a fan shape, so that they're more spread out later on the right than they are on the left, so that's no good. This is a bad model. Also, the one on the far right is no good because there's a U shape, so it kind of goes up and then down. We don't want that, okay? So is everybody ready for the test? We want the mess. We don't want this pattern where it fans out or the U shape. All right. So which model is better, A or B? So if you're online, put your answer in the chat. If you're here, who thinks A is the better model? Who thinks B is the better model? Oh, everyone passes. Thank you, everyone. Oh, wonderful. Okay, what about this time? Which one is the better model? Is it A? Everyone thinks A. Is it B? Is anyone not sure? You can have not sure. That's also a possibility. Okay, what about now? Who thinks it's A? Who thinks it's B? Who thinks not sure? Most people not sure. It's definitely B, but there is no way that you'd be able to tell from this plot. Okay, last one, just to clear our palate, because that one was a bit yucky, okay? All right, what about this one? Who thinks A? Who thinks B? Everyone thinks B. All right, so this residual plot is from exactly the same pair of models as this residual plot. It's just a different type of residual. And so I wanted to show you this because this is the kind of thing we're going to be talking about visualizing data. Sometimes when data is discrete, it matters how you treat it before you visualize it. And this makes it much easier when you do it right to see the patterns that you're interested in. So we want to, when we visualize, we want the important patterns to stand out, so the U shape or whatever. And we want to minimize these unimportant artifacts that we're not actually interested in. And so usually when we do a scatter plot, we're expecting continuous data, not this sort of discrete, funny shape things. We usually want something quite symmetric, so maybe like a normal-ish distribution, maybe even normal, standard normal for residual plots is what we expect. So these are the kind of things we want, or we expect from when we're visualizing. Okay, and so what happens when you do residuals for GLMs, generalized linear models, where you model data that might be discrete, you can define residuals in lots of different ways. So there's millions of different kinds of residuals. The ones we usually plot are called Pearson residuals, and they're those chunky ones that we saw that we couldn't identify whether things were going well or not. There's other ones, but the ones that I plotted that were nice and the way we could see the shapes, those are called Dunn-Smyth residuals or randomized quantile residuals. So I'll focus a bit on, or pretty much most of the talk on how we can use these kinds of residuals and the models behind them to make visualizations easier to interpret. Okay, so if you wanted to do this, I'm trying to put all the code for everything in the slides. So I'll give you the slides later on. So if you run a GLM, you can plot the residuals pretty easily. If you just the Pearson residuals, where you get this plot, the bottom ones use a package called Dharma, and Dharma will let you plot Dunn-Smyth residuals for almost any model that you fit. So if you want to get nice residuals and be able to interpret them for your GLMs, I'd recommend that. Okay, so that's residuals and kind of discreteness, but what I'm interested in is multivariate data. So I want to be able to visualize multivariate data that's discrete. So we'll talk about first some multivariate data. So what do I want to do? What do I want to see when I have multivariate data? So what do I mean by multivariate? I mean, I have lots of variables and I want to visualize how they fit together. So I might want to know if any of those variables are correlated or interacting with one another, but also want to know about the observations. So, are they clustered together? Are there outliers? Are there any relationships with covariates that are sort of divide things? So for these kinds of things, discrete data can, just like in the residual plot that we saw, it can obscure some of these things because it's sort of distracting the discreteness of the data. All right, so we'll start with some continuous multivariate data just to see what we want to do in terms of visualization. All right, so a lot of people will know the penguin data. It's pretty well known these days. You can get it at the Palmer Penguins. Kirsten Gorman collected it and put it up. It's a wonderful little data set of 3 types of penguins. So there's 3 species of penguin. This you don't need to see, it's just how I've handled the data in case you wanted to rerun my code, but I've just put them in columns, made them nice. Okay, so what do I want to do? So I hope you remember from primary school seeing something like this. So maybe it's high school. High school. All right, so you've got this shape. It's a 3D shape. And usually what you have to do is you have to come up with this top view, front view, side view. Okay, so that's one way to visualize this shape, is to cut it up into these different views. So those are like pairwise plots. If you have 3 variables, those will be your pairwise plots of the 3 variables. So that's one way to visualize data. You don't have to have 3D data. You can have 5D. You can still do pairwise plots in however many dimensions. Another thing you might want to do is like a PCA or factor analysis. And what happens there is you turn the shape until you kind of have as much information as you can from one direction. So that's kind of a factor analysis. So this shape here might give you most of the information about what this shape looks like. But this is a good direction. So that's what a factor analysis does. And then there's these fun things called tours. And a tour is like having a little drone, and it flies around the shape. And so you just go around and around and around the shape using a little drone. This is my personal drawing of a drone. I'm pretty happy with it, using paint. Okay, so we'll think about those three kinds of visualizations in this talk. All right, so here is my penguin data. I can use, I can do a pairs plot. You can of course use the pairs function in R, but that function is awful. So I recommend the GG Galley package. It does much nicer pairs plots. I can use sort of the coloring from ggplot and give you nice plots. So I've colored the different species in different colors. And I can see lots and lots of structure just by looking at this pairs plot. So for example, flipper length and mass are very positively correlated. So that's a relationship I'm interested in. Also, if you look at, for example, bill length and flipper length, they pretty much separate the species. So they're all the species individually clustered together. So I'm getting like a lot of information from this pairs plot about the data. Another thing you can do is a factor analysis, or a PCA, these are sometimes called. Also really easy to do in R. The Fortify library is just for the plot, the GG Fortify. The factorial, so the second line of code is actually doing the factor analysis, this bit, and that's in base R. But then you need the GG Fortify to do the nice plot. Or there's lots of other ways, but this is one way. So this is the thing where it kind of chooses a direction that kind of gives you the most information. And so it's chosen a direction where, you know, everything's kind of spread out, and you can see very easily the separation between the three species. And we can also see the variables in a particular direction. So because I've gone in a particular direction, these variables are sticking out at different directions, like the axes on my plot. And so I can see, for example, that flipper length is down here. So along the axis of flipper length, the blue, which is the chin strap, is divided from the other two, Adele and Gen 2, kind of along that axis. So that's one of the variables that sort of divides the chin strap from the other two. So you can get quite a lot of information about the data from this plot. And then if you've ever done a tour, they're so much fun. The tour package is really easy to use. So all I do is I grab my drone and I fly around in 6 dimensions, and I get to see the data from all these different dimensions. This is just one part of a tour. The tour goes on forever. It just flies and flies and flies. And I can sort of see which direction, you know, I can see a lot about the structure of the data. Of course, the colors are differentiated. You can also see like there's maybe an outlier down here, a lot going on in this tool. All right. So I want to do all of that, but I want to do it with discrete data. I want to really be able to visualize all these patterns, but for discrete data. Okay, so remember the picture of the cute penguins? You're about to get a picture of spiders. I tried to find this cutest picture of spiders, but if you're afraid of spiders, please close your eyes. These are some of the spiders in this data set. So this data set has basically a bunch of spiders in it. I think I have it. Yeah, so this is the spider data set that is in a few of the packages, NBAbund and ecoCopula, you can find it. Essentially, each variable is a spider. So here I've got one variable is a spider, and what is in the variable is how many, the abundance of that spider at a particular site. So this spider here, there was 25 of them found at this site, and this spider, there was 10 of them found. So this data is discrete, i.e. it's counts, so it can't be between 1 and 2, it's 1 or it's 2. And also what happens with discrete data is quite often there's lots of zeros. So you can see some of these columns, there's heaps and heaps of zeros. It's like very little data that's quite discrete. Sometimes it's 1, sometimes it's 2, but mostly it's 0. So this kind of data happens a lot, especially in ecology where I do most of my work. So I'd still like to visualize the relationship between these, the abundances of these spiders. So I'd like to do all that stuff that we were just doing with the penguins. But what I don't want is all the stuff that comes with discrete data that I'm not interested in, and that always comes with discrete data. So for example, skewness, discrete data is always skewed. That means there's lots of small counts, very few large ones. So that's not interesting to me. I know that's going to happen. The variance depends on the mean. So small counts are not very variable, large counts are very variable. That's not interesting because that's always the case for discrete data. So I don't care. I don't want that to be part of my plot. Of course, the discreteness. So some observations are identical to each other. So if I plot them, I'm going to get them on top of each other. So that's annoying. I don't want any of that. So I want to somehow get rid of all of that, but still get to see the relationships between variables, the relationships between the sites, and so on. I just wanted to make a quick note. The spider data is quite different to the penguin data. So in the penguin data, the columns are like things about the penguins, like their length and stuff. Whereas here, the columns in the spider data set, the columns are the individual species. So I won't be coloring them by species. I'll be coloring them by some other variable about the environment. So each column is a species. Each variable would want to know the relationships between species abundance. Okay. So here is my pairs plot of my discrete data. I'm not super happy with my pairs plot. I can see that this is very skewed, right? There's many small observations of this spider. So it's many zeros and ones, but not very many large ones. I can't see the relationship between this variable and any of the others because of this skewness. Like it's very hard to imagine what the relationship is between these two. And that's true for all of them. The ones that are a little bit more abundant, you can kind of see a relationship, but it's very hard. I can't tell if things are really clustered together. It's a mess. I don't like it. Oops. Okay, so what can I do to overcome these problems and get like a nice plot of my data? So some things that people do are transformations. So you can take a log or square root transformation, and that will do some of this, that will resolve some of these problems. So for example, the Pearson residual is a kind of transformation. So it sort of sorts out some of these issues, the mean variance, some of the skewness, all of that will kind of disappear if you do the right transformation. And it works pretty good on large counts. If you have small counts, transformations are not as useful. Then if you have ordinal data or binary data, forget it. And I'm not going to get anywhere with that. And also, you can't really know if you've done the right transformation if there's a sense of right in the right transformation, like this, you can have two different transformations and make different, like, you have different patterns, and then you don't know which one is right in some way. And then people do jittering. Jittering just means you move the points a little kind of randomly around so that they're not plotted all on top of each other. That's basically what jittering does. And you add the noise, this is called noise, and you either add standard normal or uniform or something noise so that, at least you got the points separated on your scatter plot. So that's really good. It removes the discreteness and it lets you at least see all your data, but you kind of have to use trial and error to figure out how much to move the points. Sometimes you want to move them a lot, sometimes a little bit. And then also, sometimes if you have 2 points, like y1 here is less than y2, if you jitter them, suddenly they end up the other way around. And that's kind of it's a bit yucky, not fond of that. So yeah, so there's like a little bit of trial and error going on here. Okay, so another option is to go to modeling. So modeling is a statistical name for something or other. But I guess what I mean by modeling here is you assume that your data has a distribution. So it might be normally distributed, it might be Poisson or binomial. It has some distribution, some probability distribution. Or you might imagine it has some relationships between the things. So you might do an LM or something. And then what most people do, like if you've ever been a consultant or help people with stats, you get the model, then you get the p-value. This is the point of models. So that's what happens, right? And I do it all the time too. But models are actually like wonderful things. You can do a lot more with them than just get the p-value. You've got effect sizes, you can do prediction, you can do model selection, and it turns out they can help you with visualization as well. So we're going to use models in order to help visualize data. How am I doing for time? Oh, pretty good. All right, so Dunn-Smyth residuals. So I'm going to talk about Dunn-Smyth residuals, which I briefly introduced in the intro. They're a kind of way to do a sort of more principled transformation jittering in one, using models. So like transformations, they will stabilize the variance, they will get rid of the skewness. So that's really good because we like that about transformation. And like jittering, it will remove discreteness. So it does both those things. But on top of that, we can actually check if the distribution is appropriate. So the transformation, we can check using a residual plot, have we fit the right distribution? Is the Poisson the right model for this data? It also works on all data types. So if you have binary, if you have ordinal, whatever you want, counts, all of those work fine. And as an added bonus, it preserves the ordering of my data. So the jittering doesn't cross boundaries between sort of the Ys. Okay, so Dunn-Smyth residuals were sort of presented by Dunn and Smyth, who are Australian. They call them randomized quantile residuals, which is what they are. And they've been sort of in the background. Some people have implemented them in different packages. NVIDIA, Glama, Gamels, they use these types of residuals. If you want to use them, use the Dharma package because you can just fit GLMs and use LME4 or JAGs or whatever, and it will still give you these Dunn-Smyth residuals using Dharma. So I'm a big fan. I use them all the time. So I tried to find literature on using these for visualization because it sort of seems, I don't know, in some way obvious, but in some way not obvious. I don't know. I found one paper which actually does use them, but they call them generalized distributional transform. So I'm not, yeah, I'm sure there are others. I'm certain, but I just could not find them. But there is a bit of literature about other things to do with discrete data. So for example, the mean variance relationship, the fact that small counts are less variable than large counts. It's been known for a long time that it confounds dispersion and location effects, which means dispersion effect is like how variable things are, and a location effect is where things are. So what you might find is that you identify clustering, but really that clustering is not clustering, it's just that the counts are small relative to the others, and so they're always going to be much less variable. So it might not be clustering. So there are, yeah, so, and similarly, like variables with small counts, you might get overlooked because all the counts are kind of on top of each other, they're very small, and then there's these big ones. And so when you're actually looking at a scatter plot, you can only see these 5 dots that are really big, but the patterns in the little ones you can't see. But there's other sort of things you can do in terms of visualizing discrete data like MDS plots. There's a bunch of factor analytic methods as well. So there is lots of literature in terms of generally visualizing discrete data. Okay. Maybe I'll stop for questions. Anyone have a question? Been talking for a while. Oh, yes.
I could be throwing you in the deep end here, so right.
I'm ready. I love to ocean swim.
Right. So I used lots of correspondence analysis.
Uh-huh.
I used lots of factor analysis.
Yeah.
So reading your bottom point there, I didn't know
I guess correspondence analysis, as I understand it, what you do is you take these residuals.
Oh, sorry. Can you repeat?
Oh, I'm sorry. Yes. So the question was, is there a relationship between correspondence analysis and factor analysis? So what I'm not an expert on correspondence analysis, but what I understand it is you take the residuals from like a 2x2 table. Yeah, the sort of chi-squared residuals, and then you do a PCA. And the PCA is kind of quite similar to a factor analysis. So it gives you kind of a similar plot. So what you end up in the end is like this plot that gives you sort of a ordination axes and stuff from correspondence analysis and factor analysis. So I guess that's where.
It's kind of like selected value composition type.
Yeah, which factor analysis is sort of also, but not quite. Yeah, okay. So Dunn-Smyth residuals, I'm just going to do a little thing where hopefully I explain to you vaguely what they are. All right. I went and collected some data, some counts. I counted something, some spider, I guess. Most of the sites I went to had 2 spiders, but some had 3 and 4 and so on. A few had 1. So this is my data. So about 25% had 2 spiders. I now want to say, well, these spiders are from some distribution. I'm going to say they're from the Poisson distribution. This is Poisson distributed. So I'm going to fit a Poisson distribution. I use GLM tilde1, and that's all. And say these are from a Poisson distribution. This green is that Poisson, the probability distribution function from that Poisson distribution. And that probability distribution, so this is the modeling part. I have my data. I have modeled the data as a distribution. I'm done modeling now. So the distribution, the density function in green can give me a distribution function in dark green steppy things. Okay, so how do I get the dark green from the light green? I stack them. I get this little green one here, and I stack it on top of this one, and I get to here, and then I get both of those, and I stack them on top of here, and I get to there. So I'm just stacking as I go along, and this is this. So we're done now with the hard stuff. So now I have a bunch of observations. Say I have 100 observations. Some of them are 2s. Lots of them are 2s. So each time I have a 2, I need something for that observation. So what I do is every time I have a 2, I give it a number between these 2 values on this CDF. So I go over here on the f of 2 and I give it one of these values. So if, how do I decide which one? I'd randomly get a uniform value on that red bit, and this is the value I get. This is my residual for that 2. But I have lots of 2s. I have more than one observation that's a 2. There's lots of sites where I had 2 spiders. So a different site is going to get a different residual. So all of my 2s end up slightly different, and that's the jittering part. So what you'll notice here is, all right, so for those of you playing along, if I want this to be a proper Dunn-Smyth residual, I need to transform it back to a normal. It's not important. What is important is that if I have a 3, I'm going to put it up here. So it's going to be up in this region, which is always higher than any 2. So you can see that the 2s are going to be down there and the 3s are going to be down there. So I'm never going to get that reversal. So that's really nice. All right, so how do I get some Dunn-Smyth residuals? If I don't want to use Dharma, which I don't, there's an ecoCopula package, which I've written with some collaborators, and it does a bunch of things. And one of the things it does is residuals. This code is yucky. I know that. We're going to write a package to make this a little bit simpler. So what this does is this stacked SDM is another way of saying fit a GLM to each of my columns. Each of my variables gets its own GLM. And then from each of those GLMs, I'm going to get some residuals. And then, of course, the output of my residuals function is not a data frame. So I have to fix that. I'm sorry. So this is what happens. So here is my original data, and here are my transformed data, my residuals. So this 25 becomes a positive 1.5. This 0 gets a minus 0.5. This other 0 gets a slightly different number. Okay. So now instead of plotting this, I'm going to plot that. And this is what I get. So I'm slightly happier with this plot compared to the other plot. One of the reasons is that everything isn't so skewed and stuck to itself. So that's really nice. I can see some patterns. I can see these two variables. So this species here is positively correlated to that one, which I can't see where it is. So that's really nice. I can see the relationships between variables. I can also much easier see what the relationships are in terms of the points. So the points are actually, the colors are to do with leaves. Are there leaves on the ground? So red is no leaves and blue is leaves. Apparently spiders care about leaves for some reason. So you can see that there is a fair bit of separation in some of the species in terms of how many leaves. So some of the species care about leaves. Like this one tends to have low abundance when there are no leaves and high abundance when there are leaves. So that's nice, interesting thing to visualize. How am I doing? Time still okay. All right. So, and then I can do like a tour if I want. If I want to do the droney thing to fly around my data, here I go. I can start flying around and I see these guys are quite separated from each other. And then the blue ones are all together. So the no leaves are all kind of can be separated out. But the red ones, these three orange ones are kind of more similar to these blue ones maybe. I wonder what's going on with that. Can't see any outliers. Can't see any outliers. So that's interesting. There was not really any outliers in my data. So that's basically the Dunn-Smyth residuals. So most of my research has actually not been on, but yes.
Sorry, just a quick question about the negative value that you got there. Is that because it's a
Oh, I should explain what that means. Yeah. So the negative binomial is kind of like a Poisson distribution, but slightly more, slightly wider. So this data doesn't really fit a Poisson distribution, even though it's counts, sometimes things don't work. So the negative binomial will not give you negative values. It's still a distribution for Poisson, for count data, which is always 0 or positive. The reason I get negatives is because, so what I do is, when I get the residuals, they're between 0 and 1, so they should be positive. But then I transform them back through this. So if I left them as 0 and 1, they would be uniform. And I really prefer to have normally distributed data than uniform because it's just more natural for me. And so I transform them through that to get that's a really good question. Thank you. I should have pointed that out. Okay. Okay, so so that was kind of Dunn-Smyth residuals are really useful in many ways. And the way I came across them is actually in my PhD, I looked at copulas, and copulas are quite related to Dunn-Smyth residuals. So I'll go a little bit into them because they will also use them for visualizing things. So when you have multivariate data and you want to build a model for all the data, so rather than looking at one species at a time, you want a complete model for all of your variables at the same time, you've got a couple of options. So you can do hierarchical type models. You can do generalized estimating equations, which is not quite a model, but it's a way to model that data. Or you can use copulas, and copulas are not very commonly used except in finance, but really super useful. And so the Dunn-Smyth residuals is like an intuitive way to understand copulas. And what I'm about to say is wrong, but intuitively correct, but technically wrong. So here is like how to think about fitting a copula. What you do is you take each of your columns, each of your species, and you just fit a GLM to each of them, and you calculate the Dunn-Smyth residuals. So now you've got some Dunn-Smyth residuals. Each of those will be normally distributed. So if the model fits correctly, each of those will be normally distributed. We know that from theory. They won't necessarily have a joint normal distribution, but that's what we're going to assume. We're going to make the assumption that these have a joint normal distribution, and then that joint normal distribution will have a covariance. And so we're going to think about that covariance as sort of covariance for the data, for all the variables together. And then you can use that covariance matrix to sort of do factor analysis or graphical modeling or stuff. Like I said, this is not quite right, but intuitively, that's kind of what happens in a copula. If you're a stickler, this is what actually happens. So, so each of the variables has some marginal distribution. We're going to call them F. For example, the Paramount spider has some, maybe it's Poisson distributed with a mean 3.5. That's the distribution for that spider. Each spider has its own distribution. And then we think about some latent variable Z, which does have a multivariate normal distribution. This underlying latent variable Z has a multivariate normal distribution with some covariance matrix sigma. And this Z gives rise to our discrete data by first taking phi of Z to get something uniform and then back transforming it through the cumulative distribution function to get our discrete Y. So you start from the latent variable Z and you go back to get the Ys. And if you do it this way, you get what is called a Gaussian copula. And then you can estimate it any way you like. But this correlation matrix, this covariance matrix, can then be used to do various things. So that might have been like way too much information for some people, but hopefully it makes sense to a few of you. Yes, so we use that correlation matrix. So this is what I do in it's this ecoCopula package. So we fit Gaussian copulas in this way. And most of what happens in this is this chord function. So chord stands for Copula ordination. I don't know if ordination is a term that people often use for things like factor analysis and PCA and all of these kinds of methods. And so, so what I do is I've got my spiders, and then I fit the ecoCopula package will fit a Gaussian copula that has a factor analysis on the latent variable correlation matrix. And so using that, I can then plot the output of my factor analysis for my spiders. So what do I see here? Well, these spiders over here are, they like leaves. I think they like leaves. And these are them. These are the couple of spiders that really like leaves in these sites where there are lots of leaves. And on the other side, on the opposite side, these ones don't tend to like leaves as much, although some of them do. But these guys, anything down here doesn't really like leaves. So Paradiglu is not a leaf lover. So that's one way to look at this great data. How am I doing? Still good. Oh, it's all good. I was sure I was going to go away. Okay, so now I'm just going to show you some like prettier plots because I like to. So I have some ordinal data. So people go, ecologists, they go and they look at like a plot, like a 1 square meter plot. And they go, what proportion of this plot is covered by this first plant, Bob or whatever. So Bob covers like maybe, I don't know, 5-ish. So they don't want to give a number for the cover because they're just looking at a plot. So they put it into categories. They're like, okay, well, this one is 0, but this next one is, there's more than nothing, but there's probably less than 20%. And then they have another category from 20 to 30% and so on. So they'll go, okay, it's 30% that one. So it just ends up in a bunch of categories, which are ordinal. Okay, so this is what they've done here. And I've just, done some yucky things to get the data into shape. And down here, I've created some Dunn-Smyth residuals as well for this data. Okay, so first I'll plot the raw. Okay, this is what it looks like. So one is actually 0, because ordinal data often starts at a 1. So 1 is actually the category that means there is nothing there. So this species tends to be not anywhere very much. This species is always at like 40%, oddly, just likes to be at 40%. So this is kind of what the data looks like. So if I do a pairs plot, what happens? Everything is on top of each other. So I've colored this by elevation. Elevation is an important predictor of different species and where they go. So purple is high elevation, orange is low elevation. I cannot for the life of me tell you anything that I'm getting from this plot, except that I don't know. So the purple ones, there's lots of purple ones, but is there orange ones underneath? I have no idea. I don't know. But if I just plot the Dunn-Smyth residuals, I get this plot, which I like much better. So I can see now sort of patterns. So the second species, arcpat. So these are all like contractions of the species name and the genus name, so they're none of them make much sense. But arcpat seems to be positively correlated with CMR. So that's like super exciting because I could not see that there. So you can see patterns in like how elevation is related. So this species is at low abundances. So the top is low for the species, and low abundances in the purple ones, which means at high elevations it's at low abundances, and then at lower elevations it's higher abundance. So that's really interesting. Yeah, so that's cool. I can also use the ecoCopula package to do an ordination of this, even though it's ordinal data. We can model ordinal data with cumulative link models, which are kind of like GLMs. So that's not a problem. And I get this very nice ordination plot, so I'm very proud of. Here is the code. It uses ggplot. Anyway, here is my lovely elevation gradient. So there's the high elevation sites are all over here. And these are all the species that tend to like the high elevation sites in this direction. And then there's the low elevation sites are here. The kind of middling elevation sites are all up here. So there's one gradient in this direction which separates the high from the low. And then there's another gradient which separates the sort of middle ones. The lighter ones are sort of in the middle from these ones. Super interesting plot of this data. And I think I'll probably end on that. So that's my references and my acknowledgements again. Thank you everyone for listening.
For a wonderful talk. And we'll take a few questions from the audience. Okay, first question is, get reference up. Nick.
It seems to me
Ranks, yeah. Ranks are another one. Sorry, I have to repeat that. So I'm going to a lot of trouble when I could be jittering and then doing ranks. Yeah, ranks are kind of quite related to these residuals. So if instead of using like a Poisson distribution, I use the empirical distribution function, then I would get the ranks. That's essentially what I would have. So they're quite related sort of things. The jittering, you're absolutely right. You can just jitter it. I quite like the Dunn-Smyth idea because the jittering is sort of appropriately high or low, like the amount of jittering, you don't have to think about how much. But yeah, you're right. I mean, you're absolutely right that you can do the ranks. I've never really done it. Whenever I do it, I just end up going, oh, have I done it right? Yeah.
Yeah, I usually think about the Copulas chapter is that if the student is more than confident, you can calculate correlation risk, not very correlation. Popular transformation of Copulas chapter is not very cool.
Yeah. Yes, yeah. So if you what you want to know is just the correlation between your variables, you're absolutely right. I guess what I kind of want to do is more than that. So I want to do like ordination, like I do factor analytic things. Also, there's like graphical models, other things that you can do when you have a full correlation matrix, which yeah, no, I think you're absolutely right. Sorry, I should have repeated the question. Kendall's tau can be calculated without necessarily fitting a copula. And so you can get correlations between things much easier than what I'm doing here.
But the point is that there's a no relationship.
Yeah, that's right. Yeah. So you're right.
Question in the chat.
Okay, thank you for the great talk. I was curious about the index on the tour scroll bar. Does it have an interpretation or is it just an ordering? Yeah, no. So the tour package picks a random point in space as if you just like threw your drone anywhere in particular, and then it picks a random direction and it goes in that direction. And then after a while it stops, and then it picks another random direction and it goes in that direction for a while. So if you run the tour, it just kind of wanders around in space. So it gives you something smooth, which is really nice because you can kind of feel like you're going around. It's because it kind of picks these 2 points and then smoothly goes between them. I hope that sort of answers the question.
Any questions?
With that, I was really fascinated with that tour thing. So we set up things in spot space to kind of make a 3D representation and then pick a point. Was it actually just randomly going in 20-dimensional space and going over there?
It goes in 20-dimensional space. It picks a point in 20-dimensional space and another point in 20-dimensional space, and then it makes a smooth path in sort of the 20-dimensional sphere around those 2 points, and it kind of does a smooth path.
So trying to keep the distances, like kind of like how NVS tries to keep the distances.
No, it doesn't do anything like, it's literally a projection. It's literally just turning, but in 20, it's just hard to imagine in 20-dimensional space. But in 3-dimensional space, it's as if it's just flying around. But in 20D, it's just literally flying around as well. It just doesn't care about us only seeing 3 dimensions. It's quite happy.
Okay, because I'll ask the questions. How does the Dunn-Smyth Residual work for ordinal data?
Oh, you fit a cumulative link model.
Okay.
So, and then you just get it from that. So all you need is a distribution function. And once you've got one, you're good. So you fit any model that makes sense of ordinal data cumulative link is what we usually do. Or some other model. I don't know. Are there other models for ordinal data? There probably are.
Right. Any other questions? Okay, if there's no other questions, then we'll wrap up tonight's talk. Please join us and thank you. Thanks, Gordana, again for a wonderful talk tonight.
Thank you.